So, hello, I am your host Himel again. Welcome to Linear Algebra for AI and ML. Today is our day 10, and as we all know, that we are continuing our marathon from day 7 to day 12. Our marathon will be finished in this Friday. So yeah, it is your host Himmel, currently studying at Bragg University in first year. This whole session is supported by Global AI Community, Dev Changemakers, NSDC, and TensorFlow User Group Bangladesh. So, what were the contents and what we're going to learn today and what we're going to learn tomorrow and the very next day. So on the day 7 we learned about basis, we learned about the orthogonal vectors, we learned about orthonormal vectors, we learned about generic tensor notations, and on the day 8 we learned about tensor transposition, basic tensor arithmetic, tensor reduction, the dot product, and we learned how we can use numpy for this. And yesterday we learned about solving linear systems with substitution and elimination, and we also learned about the Frobenius norm. So in these three sessions we learned about these things, and also we learned how we can solve this with help of numpy. Our numpy are uh, data science program from Python, which is helpful for us to solve these machine learning mathematical problems. So in today's session, or we are almost in the conclusion of our marathon. Today we will learn about affine transformations and eigenvectors and eigenvalues. We learned about some of eigenvectors and eigenvalues on the matrix part. We learned how we can do a singular value decomposition. We learned about how we can do LU decomposition. We learned how we do the PLU decomposition. While doing that, we learned about eigenvectors and eigenvalues. There we used the mathematical parts. Now today in today's session we will learn something more about in-depth or more of a theoretical definitions. So, and tomorrow we will be learning about eigen decomposition, eigenvector and eigenvalues application. And on the last day, or our concluding day in this Friday, we will be learning about data compression with SVD or singular value decomposition and the Moore-Penrose pseudo-inverse. So, as I said earlier, today our contents will be our affine transformations and our eigenvectors and eigenvalues. So, let's jump to our today's session. So, what is affine transformations? So, by the definition, an affine transformation is a linear mapping method that preserves points, straight lines, and planes. It includes transformations like translation, scaling, rotation, and shearing. It also involves scaling, rotating, and shearing the coordinates, which we will see in the code demo. And it also adds a constant vector to every point. So it is more likely like axis wise, like as we learned earlier in the linear algebra or in the systems of linear equation. This was our x-axis and this was our y-axis. Here we learned about how we can implement or how we can put our dots or our numerical digits in these coordinates. We learned about how, if we find in the last session we learned about how we can do the elimination or how we can do the substitution. We get some coordinates like 2 comma minus 6, or let's assume we got 2 comma 5. So how we put these dots in the coordinate form in our this plane. let's assume for this one, let me change my color. Let's assume here we have 1 2 3 4 5 6. We got here again 1 2 3 4 5 6. So if I have a origin of here, here is our origin 0. From here, for this one, we will be get in the x-axis, we will be going at 1 2, and for the y-axis, we will be going in the negative axis, right? So 1 2 3 4 5 6 7. So we will be going here, right? So if I draw a straight line from the origin to this point, this will be my coordinates of 2 comma minus 6, right? So again, let's do for another value. Let's do for this one. Here I have a number 2 in my x-axis and I have number 5 in my y-axis. So let's put this right here, x-axis 1 2, and for the y-axis 1 2 3 4 5, right? So it goes here. So from my origin to here. So this is for this one, and this is for this one. So this was how we can map our coordinates in our axes. So now let's look at some code demos, right? So as we learned earlier, we learned about numpy. At first we will import our numpy as np. It is imported. Now we will define an array. We are defining an array in v, in this variable np.array. Here we got 3 comma 1. Now when we run this, we will get our array of 3 comma 1. Now for this one, for this plotting purpose, we will be using matplotlib. It is one of the another what is this called? This can I forgot the name at this moment, but this is another kind of thing to solve these mathematical problems, and we can find this in interactive ways, or how we can do this interactively more. So now we import this one. After importing, we are defining a function or a plot vectors. Here we will pass two parameters. We will be passing vectors and we will be passing colors. So why we are passing vectors? Here in these vectors we will be passing our this one. Here we will be getting our axes, or we will be getting our coordinates, and on the colors part we will be seeing the color of the line or color of the straight line. Like here we have done this line in the green color, this one in the purple color, same as here. By passing through this parameter, we will be passing a specific color to highlight our straight line or our curved line. Okay, so now while we run this function, let's run this one. It will give me no output. And now here comes where when we are using this function, right? So when we are using this function, here we are passing a vector. We are passing this vector. We are passing this vector, right? So our vector is 3 comma 1, and we are passing it through a light blue color. So what is happening here? When I am passing vector, it will call this vector or this array. It will call this array, this, it will plot this array. And what will be the color of the array? This will be highlighted in the light blue color. And what we're doing here, we are in the x-axis our limits will be in minus 1 comma 5, and the in y-axis we will be doing it minus 1 comma 5. So when I run this, voila. So it is becoming more interactive, right? So you can do this in many ways, like let me change the values in the x-axis. Let me increase it to 10. So yeah, we can see that it was in the previous one, this was from till here, right? And now we are getting it far from here. So you can increase and decrease the limit size in this, like plot.xlim. It limits the for xlim, it limits in x-axis, and in the ylim it limit in y-axis. So now let's do this again with another array. In this time we're doing this with an identity matrix. So we all know what is an identity matrix, right? We have learned about identity matrix. In the trace there is only one and the other elements will be 0. So we're after running this, we are now doing the dot product. We learned how we can do the dot product, right? So we're multiplying our I, or this identity matrix, with our previous array. While we do this, we will be doing np numpy dot multiplication dot product of I comma v. We will be multiplying our I with this v. So this will give the output of the dot product. So yeah, we found the dot product of iv. It will be 3 comma 1. Let's see if it is equal v or not. Yeah, it gives me true. So for both elements we can say that the iv and v is fully equal. Let's check out. Here in the iv I got two elements, it is 3 and 1, and in the v I got another two elements which is also 3 comma 1. As we can see here, these two elements are same, and or the dot product of here and the value of v is same, so we can see that these values are equal, or these values are same. Now let's plot our this one, our iv, in our here, like here, as we did earlier in the plot vectors. We plotted the v vector. Now we will be plotting the iv1. So how we can plot the iv1? As we have done earlier, we're calling our plot vectors function. We will be passing our iv vector, or this one, and we are passing a color. While we do this, we will get another plot. Here we can see that we have denoted it or highlighted this one with yellow. So we got the value. So what was the number? The number was 3 comma 1. Here 1 2 3 in x-axis and 1 in the y-axis. So this was our value. Now let's again do this one, but now we are not using the identity matrix. Now we are using a non-identity matrix. So when I run this non-identity matrix, it shows me the non-identity matrix 1 0 0 minus 1. And again we are doing the dot multiplication non-identity matrix with our previously, at first we have seen the array our 3 1. We are doing the dot product. We will be getting an array of 3 comma minus 1. So now let's again plot these vectors, right? Now here comes the twist. For this one we are passing, in the vector part we are passing two vectors, right? Here we are passing our v1 and the niv1. So for the v1, it will be highlighted with yellow one, and the niv, or uh, vector dot product with a non-identity matrix, it will be highlighted with blue color. So when we plot this one, our yellow part, or our v, will be going up, and our n underscore iv will be going down. Our ni we got earlier, right? This was our v1, right? This was our v1, and again this was our v1, and this is our new one, our niv. Now let's do this in affine transformation. Affine transformation, it rotates the whole thing, right? So let's do this again. Here we changed the dimension of the matrix, and we're doing the dot product. And when we are using or plotting these vectors, now you can see that it changed, right? It was going in the all the way from y to y bar in this axis, or and now it is going here. Now let's do another one in the last part. So yeah, so here I have another array of -1 comma 4 and 2 comma -2, and in the second we got np dot of dot product of a and v. Here I am getting the array of 1 comma 4, and finally we're plotting the vectors in here, the v1 or the first vector and the av1 or the newer vector. The v will be highlighted in gray and the av1 will be highlighted in red. So when we plot this, we get this one, right? So here I have nothing under 0. So what can I do? I can change the value of y-axis. Let's change this to 0. So let's see what happens. It vanishes. Now let's get it back here, and let's try to change this one. Yeah, now it is perfect, right? So here I am plotting this in a shorter area. So what we have learned in this affine transformation: we learned about matplotlib. We learned how we can plot a vector in a vector space. We learned how we can draw the vectors in the axes. Now let's move back to our slide. Now, as I said earlier, we learned about eigenvectors and eigenvalues in the practical part in the matrix, but we didn't learn the theoretical part. Now let's look at the definition of eigenvalues and eigenvectors. So what is eigenvector? Eigenvector, it is a non-zero vector that changes only in scale when a linear transformation is applied. And what is a eigenvalue? The scalar by which the eigenvector is scaled during the transformation, it is called the eigenvalue. So what is the note here? Here when a linear transformation is applied in a non-zero vector that only changes when you are applying a linear transformation, it will be called a eigenvector. And where the eigenvector is scaled during the transformation, it will be called a eigenvalue. And eigenvalues can be both real number, or it can be complex number. It can be any integers, it can be a floating number, it can be a complex number like 2i, it can be root over minus 2, or it can be anything. So, and the eigenvectors corresponding to distinct eigenvalues are linearly independent. We learned earlier that eigenvalues are linearly independent. And a matrix with distinct eigenvalues is diagonalizable. Now let's move on. How we can compute eigenvalues and how we can find eigenvectors. When we were doing the decomposition part, we learned how we can compute eigenvalues. I show that practically by doing math problems, and how we can find the eigenvectors. We also saw that to solve the characteristics equation to compute the eigenvalues, it will be the determinant of A minus lambda I, or the identity matrix, will be equal 0 for the lambda. And to find the eigenvectors for each eigenvalue lambda, the solve will be A minus lambda I multiplied by V will be equal 0 for our vector V. Now, we learned about the eigenvectors, we learned about eigenvalues. Many times we got questions in our head, right? So we're learning these things. What will be the uses of this? Many of you ask me why we're learning this. This is no meaning here. It is totally not useful. This is like rubbish, and many more questions. So now let's look at why or what are the applications of eigenvectors and eigenvalues. So at first we can see here, let me change my color of the pen. So yeah, at first it will be helpful to stability analysis. In systems of differential equations, eigenvalues determine the stability. When you will be doing analysis with big data or various data, eigenvalues determine the stability. And on the second point, principal component analysis, or PCA, when we will be doing the statistics part, eigenvectors identify principal components. The principal components will be identified with the help of eigenvectors. And when we will be learning quantum mechanics, if you find interest in quantum mechanics after learning machine learning or AI, after studying these things, if you want to learn about quantum mechanics, eigenvalues and eigenvectors describe the states and observables in the quantum mechanics. Also, in the vibration analysis in mechanical system, eigenvalues determine the natural frequencies. The natural frequencies what will be available, it can be determined with the help of eigenvalues. And finally, in the graph theory, eigenvalues of adjacency matrices reveal properties of graphs. You can find the properties of graph using eigenvectors and eigenvalues. So yeah, this was from my side in today's session. Hopefully everyone understands the concepts of the affine transformation and the concepts of eigenvectors and eigenvalues. The whole videos will be uploaded on my YouTube channel and on my Facebook profile. You can find the videos from there. Thank you everyone.